of time steps of the unit hydrograph is given by the number of measured direct runoff time steps minus the number of rainfall pulses plus 1. That should give you the total number of pulses. The number of pulses for the unit hydrograph. Yes, so the question was how there is a point, I don't know whether it is here. No, it was previously. And I told you that I was going to check it and explain it how it is done. Could you give me a minute? I just take some water. Yes, so when you follow the example, you will derive the unit hydrograph. And this is the convolution approach. In order now, once you have a unit hydrograph, and that is what I explained last time, when you have excess rainfall, then you can, and you have the unit hydrograph, you can apply the convolution. You can apply the convolution to derive the discharge. So you have calculated this unit hydrograph. You can always, and if you have excess rainfall, let's say you have measured rainfall, you can just apply a unit hydrograph and then calculate discharge at a certain point. And I will show you that. And still today, you will still wait. You will still wait about that. About this part, why we have these where we have three terms, why we have three terms in each of the equations calculating the unit hydrograph. That one I will still explain to you. I've not really looked at it yet. And the only issue is I just forgot how it is done, and I will explain it. I'll make sure I have to write it down. Otherwise, if I don't write it down, I will not remember the next time. So it has to be written somewhere. Where we have, I need to. And what I'll do about this explanation, I will probably even record it and share. I'll record it and share so that we do not waste another time, any other moment in there. Yeah, so now the one principle about the unit hydrograph, and if you want to check whether you have done it correctly, the depth of direct runoff in the unit hydrograph should be equal to 1, should be equal to 1 unit, depending on the kind of units that you have done. Here, in this case, the units were inches, so when you add the depth of the unit hydrograph, this is the unit, the depth should be equal to 1. And how do you determine the depth? Let me first go back and see whether that information is given. Here is our whatever, the question, excess rainfall hydrograph. How do you get the depth when you have the area, when you have the discharge? And I'm seeing I did not give, there's something I did not give here. Normally you can check whether the depth is 1 unit. And how do you do that? If you are calculating a unit hydrograph for, let's say, a certain river, for a certain river, this is the river. This is the river. So you have this river and then you have the catchment. And you have been calculating discharge at that point. Let's say you are calculating the discharge here, Q, at the exit of the catchment. The discharge is usually a volume that is flowing per given time. So if you multiply the discharge by time, you get a volume. Now, this particular volume is being generated from an area. So imagine you are looking now at this catchment. S is a reservoir. And if I can try to draw, I don't know whether I'll manage because because it has to follow. You imagine it as a catchment because now it has to, I'm trying to draw a 3D kind of. So the discharge, if this is a volume and it is coming from this area, in order to calculate a volume, you assume the discharge, if you can distribute the discharge all over this area, if you can distribute it, what depth can it fill? What depth of the catchment can it fill? And that is the depth of runoff, the depth of direct runoff. And this concept of depth of direct runoff, we probably used it when we were calculating excess rainfall, because using the various methods, whether it is the runoff coefficient method or the fire index method or even the SES method of rainfall abstractions, we have to convert all the input data into the same units, because one rainfall is in millimeters, discharge is in meters cubed per second, and you have to convert it into consistent units. And this is how you convert a discharge into a depth. You assume the discharge is flowing over an area, and you now distribute that volume over that area. So once you do that, and let me just check what the area for this part is. Once you calculate the area, you get, once you divide by the area, you divide the volume by the area, you get the discharge in millimeters. I'm trying to check what the area for this particular catchment is. Here it is not given anyway. It is not given. Anyway, but that is the reasoning. We are going to come across such kind of a thing, and you will see what I'm trying to say anyway, what I'm trying to say. So in general, solving the unit hydrograph or calculating the unit hydrograph is solved using a number of 4 steps. You assume a unit hydrograph and apply it to excess rainfall blocks of the hydrograph except the largest. Now, another thing that I did not say, and I did not explain, and let me check whether we can see that. When you are developing a unit hydrograph, they have another characteristic. They are really dependent on the time step that is applied. And for example, what we generate from this data is a half-hour unit hydrograph. You can also develop a 1-hour unit hydrograph. And even from this half-hour unit hydrograph, you need, using the principle of, there is solution that the multiple of this solution is also an answer. I don't know whether it is a superposition or whatever. You can derive the 1-hour unit hydrograph from this. You can derive 2-hour unit hydrograph from this, but it is very important. It is very important when you are given a unit hydrograph, you have to know it is for what time step, because also if you have your direct runoff in different time steps, then you have to make the unit hydrograph to have a similar time step as the measured discharge. So that is one. So you assume in order to obtain a unit hydrograph, you assume a unit hydrograph and apply it to excess rainfall blocks. Then subtract the resulting hydrograph from the actual direct runoff hydrograph. Then compute the weighted average of the assumed unit hydrograph and residual unit hydrograph. And then repeat the previous steps until the residual unit hydrograph does not differ by more than a permissible amount from the assumed hydrograph. And why is this happening? Because the unit hydrographs obtained by solutions of the set of equations in the table that I gave for different rainfall pulses are usually not identical. And you can get a unique solution. You can get a unique solution by applying a method of successive approximation. And in this course, in this particular class, we are not going to try to obtain a unique unit hydrograph, but we will just dwell on deriving a unit hydrograph and applying a unit hydrograph. Normally, assuming we were to go to and get a unique solution, sometimes you may find that the resulting solution of the unit hydrograph may show erratic variation and even have negative values. And normally, if that occurs, you just fit a smooth curve into the data, into your data or into your graph of unit hydrograph. Some of the reasons, some of the explanation for this erratic behavior is due to non-linearity in the effective rainfall direct runoff relationship in the watershed, and also the observed data. Secondly, the observed data may not be adequately reflect this. Now, why? Because we said, and I've insisted before that most of these hydrologic phenomena, hydrologic flows in the catchment follow the linear model. And what is a linear model? I will repeat, a linear model is a model where the discharge and storage are related, are related in some sort of a way. And we said in hydrograph S, storage is equals to K, a constant times Q, K times Q. And normally it decreases. The K causes the Q to, decrease in an exponential manner. But other things will affect this. Many things affect this storage discharge relationship. For example, in a catchment, you may have depressions. And if you did when you were doing engineering and hydrology 1, looking at the various components of the hydrologic cycle, you came across depression storage, for example, water that is stored in depressions. And that water does not either infiltrates a little bit of it or the rest evaporates back. So that amounts to extra water lost, which would have otherwise translated into overland flow. So that is one of them. Two, another thing could be different land types, different soil types, and such kind of things. And, that will affect the smooth linear relationship of storage versus discharge. So now we go to the unit hydrograph application. And then we see how we are supposed to calculate the discharge. So now, if you have this equation, and let me go back to it. No, it's not here. If you have this equation, and you have already calculated a unit hydrograph, it's fully solved, and on the other hand, you have the rainfall pulses. How do you calculate Q? So I think I said calculating unit hydrograph is convolution and QN is deconvolution. No, you calculate unit hydrograph using deconvolution. You calculate the unit hydrograph using deconvolution and QN using convolution. So QN is direct application of the convolution equation. By basically just multiplying rainfall by the unit hydrograph. And let us see then how this is applied. And it will require that explanation I was talking about. And these are the steps. Number one, you select a rainfall hyetograph, estimate the abstractions, and then calculate excess rainfall hyetograph. And all of this we did in engineering hydrology 1. And something I have just mentioned before, the time interval used in defining the excess rainfall hydrograph ordinates must be the same as that for which the unit hydrograph was specified. So you have to know first the time step for the unit hydrograph, and ensure your excess rainfall ordinates have been calculated using the same time intervals. Then you apply directly the discrete convolution equation to yield the direct runoff. And after you have done that, if you want to get the total discharge, you can now add estimated base flow to the direct runoff to get the stream hydrograph. I don't know if we are already together at that point or any person has a question about this procedure. The last three are obvious because we did them in engineering hydrology 1. The only new thing here is section D because E we are supposed to be able to do it from engineering hydrology 1. So we have an example. And I will still leave you people to look at it. This is direct application of the unit hydrograph. The direct application of the unit hydrograph, the convolution equation. Convolution equation. And finally, this is the total. This is the total calculated from the previous figure. So you will go through the example. Which is the example basically applies these formulas. It applies these formulas. And today I'm teaching with still a lot of sleep. Anyway, so there are other methods of deriving the unit hydrograph. You apply you write a matrix for the deconvolution equation. You can use linear regression. You can use linear programming to calculate it. But really, it's one of the easiest things to calculate manually. So most of the times that is not really necessary, although you can apply the matrix. And especially if you are programming, then matrix becomes very appropriate so that you can write an equation for solving the matrix in a program. Now, other types of, did I even give the matrix solution? No, I didn't, and it is really easy. I should have should have. Maybe I should modify the note and add the derivation using the matrix. But you can try and derive a matrix from this. Yeah, from this. You can try and derive a matrix from this, and how it will be written. You will have rainfall. You will have rainfall, the matrix of rainfall, and this is usually the largest matrix. It is usually it's kind of a diagonal matrix. It will end up to be like a diagonal matrix. Then you have the unit hydrograph for, a matrix. You multiply, but with a matrix, a vector matrix of the unit hydrograph, and the result will be a vector matrix for discharge. So you have a diagonal matrix for P. You have a vector matrix for U, and then you multiply the two, you get a result for a vector matrix for Q. I probably, when I will be explaining that, I will give a little bit of the matrix so that that one is easy. The linear regression is what I will not write. Linear programming I will not write because it's already too easy to solve manually. So we have what we call synthetic hydrographs. And what are synthetic hydrographs? Normally, if you develop a unit hydrograph, let's say for a river, or even for the Nairobi River is a tributary. I don't know it is a tributary of which main tributary of a river. So it is a tributary somewhere of a river somewhere. If you develop a unit hydrograph for that tributary, you can only use it for that river only. You can only use it for that watershed. And also for the point of the stream where the stream flow data was measured. What am I trying to say here? If you have this catchment, example, and you have this rainfall, you have this river that is flowing in this catchment, and we are measuring discharge for this catchment here. We are measuring discharge Q at this point. We are measuring discharge Q at this point. Or let's say we also have measured another Q. Let me call this Q2. Q1, and also let's say we have measured another Q here, Q0. And then finally, we have measured, because in a catchment, you find many times we measure many places. And this Q here is for this branch. It's not for this one. It's not a combination, or you could say it's just a combination of that. Now, remember, the catchment for this point will probably be something like, the catchment for this point will probably be something, all this part here, all this part up to the watershed, the watershed boundary of the entire catchment. For this point, the watershed will probably be now all this part. And then the watershed for this point is the entire part. And you can see the watersheds are becoming larger and larger as the river flows downstream. Now, and you have calculated a unit hydrograph using this data for this particular, catchment, you have calculated another unit hydrograph for this, that particular unit hydrograph you have calculated using that data can only be used for this area. The other one for this, it can be used for that area, the whole of it. And you cannot say because this subcatchment is within this catchment that you can use the unit hydrographs generated for, universally for any part. And not only that, if you have another river, you cannot use a unit hydrograph in another river. And because of that, this poses a challenge. Anytime you want to develop, you want to calculate a discharge without measuring discharge, you have to calculate a unit hydrograph. It becomes a challenge, especially in areas where the rivers are not gauged. And that applies many times because we can only have so many river discharge stations. So normally the synthetic unit hydrographs, and we are going to see a number of them, they are used to develop unit hydrographs for other locations on the stream in the same watershed, or so now with a synthetic hydrograph, you can develop a synthetic unit hydrograph for another location within the same stream watershed, or for nearby watersheds of similar character. And when we say similar character, what are we talking about? Watershed have a number of characteristics. For example, we have the law of linear we have, for example, the bifurcation ratio. We have the stream network, the stream order. We have things like, I'm trying to remember. There are many things. There are many relationships based on areas, based on the lengths of the streams. We have, for example, the Horton's law of stream numbers. I have said already the bifurcation ratio. We have the law of stream areas, or basically, or essentially, geomorphological characteristics of the stream. That number one is the geomorphological characteristics. And then the other similar character is the climate. For instance, you cannot, we have, for example, streams in the western flowing to Lake Victoria, coming from the Kenya highlands. You know how the relief of Kenya is more like a pyramid, whereby in the middle is the highest point. And where is the middle? We have central, and the area around Aberdares, and then outwardly, the pyramid decreases in all the directions. And if you look at a DEM model of the country, that is what a 3D DEM model of the country, that is what you would see. If you can render the Rift Valley, that is what you'll see, that the center is elevated and the relief decreases as you go away from the country. And when you look at the western part, that one remains relatively higher, but the elevations as you go to the northern part, as you go to eastern and coast part, the elevations decreases. So rivers in the western, those areas are usually subhumid kind of climates. The Lake Victoria area basin, highlands and subhumid climate. And when you look at the river flowing in through the Yatta Plateau, flowing through semi-arid regions, those are two different climatic regions. And then even flowing towards the coastal area, those are two, you'll find that those are rivers with different characteristics. So if you are to develop a synthetic hydrograph, the application should be in watersheds that have the same characteristics. Now, let me try to explain the geomorphology a little bit. For those of us who come from Naivasha, or who come from Narok, or who come from the Rift Valley, the rivers flowing, let's say, to Lake Nakuru, the rivers flowing to Lake Naivasha, the river to begin with, the slope from the escarpments into the lake is very high, extremely very high. And when you look at the slopes, like I know in Naivasha, most of the areas may even look like bare, rocky, and what have you. Compare that with a river, for example, River Yala. Compare that with a river, for example, the river, which is gently sloping, which does not have very steep slopes. Now, and these steep slopes, especially in those areas, Narok, Naivasha, those are the ones that cause flash floods in places like Hell's Gate. In Naivasha, there is a stream in the city itself, yenye huwa ina flood mostly, and that happens because of these slopes. As soon as the rainfall falls, the slopes and also the soil characteristics, as soon as the rainfall falls, rainfall runoff, storm runoff is generated very fast, and because of the slope, water flows very fast. And you have had cases of situations where people have been killed in Hell's Gate due to flooding. So those are what I'm talking about, similar characteristics, similar character. So you need to be able to know, and this is something probably we saw during engineering hydrology 1, characteristics of, especially the geomorphological characteristics of streams. And there are 3 types of unit hydrographs. One, those relating hydrograph characteristics. Hydrograph characteristics, that is 1, peak flow rate, base time. What is a what is that we are talking about? If this is a graph of a hydrograph will be something like that. And this one I'm drawing a direct runoff hydrograph. We are talking about the peak flow rate. This is the peak flow rate. And then we are talking about the base time. The base time is the start, the time between the start and the end of the direct runoff. That is the base time. And so the hydrograph relates, the relation is between those characteristics and watershed characteristics. Those characteristics that I was talking about. Is it climate? Is it the geomorphology? Then there are those based on a dimensionless unit hydrograph, and we shall see. I don't know whether I have that. I don't know whether we did that. And we have the third one. Those based on models of watershed storage. So we already have the dimensionless unit hydrograph, and then those based on watershed storage, and we have not done those ones in this particular course. So we are only going to be looking at 2 types. We are only going to look at 2 types of synthetic hydrographs. And one of them is Snyder's unit hydrograph, and the other one SES dimensionless. Did I do? Yes. We only have the Snyder's and then the SES dimensionless unit hydrograph. We are only going to look at two, Snyder's, and then the other one, let me see it. Yes, it should be here. No, it should be back a little bit. The SES dimensionless unit hydrograph. So that is what we look. Only those two are the ones, the only two types of synthetic unit hydrographs that we are going to look. And if we can start with the Snyder's synthetic unit hydrograph, and at this point, probably we take a break so that I also make a cup of coffee so that we can get on to it. And any question, and kindly remind me, all of you, whoever, keep on reminding me because I need to explain the convolution equation and convolution further. So keep on reminding me so that I can send the recording because the questions that I don't know whether I send tutorial questions for you to solve them. You'll be able to develop. We will be able to develop those equations by ourselves. We will be able to develop them by ourselves. So I don't know. Have I sent tutorials? Have I sent tutorials so that we can be able to stream flow hydrograph? I've not sent. I will be sending also examples of the tutorials. I may modify them in future, but we can already start doing some of the tutorials. So I want us to take a break, 10 to 15-minute break. And before then, I want to start a poll, and I see who is sleepy like me. So, like we have Brian Bisonga. So we have Brian Bisonga, John Macharia, Shibega Gilbert, Victor Kangor. Hao ndio hawana sisi. Those ones are the ones wenye hawana sisi. Wako tu wametupeleka Mwethia. I don't know if any Kamba is here. They know what I've said. They have just taken us for a ride. So let us take. We are now at 07. We can come back after 15 minutes. That will be about 8:25. We can come. Victor, you voted very late. The response time, there was a delay. Ni kama tu bila hydrograph iko, there was a very big lag time. So you only responded when I called. But I've just made a snip of who those people who were not there, so that we can have a record of the same in our WhatsApp. So let us come back at 8:25 so that we can continue. With the Snyder's unit. particular hydrograph was developed based on empirical study done by, it is named after the person who did it, that is Snyder in 1938, and it was modified by USCE, US Army Corps of Engineers. So that is the Army wing that engineers in charge of responsible for probably civil engineering. And they develop a relationship between what we call a standard hydrograph, shown in figure A, and the required hydrograph shown in figure B. And according to them, first, a unit hydrograph, a standard unit hydrograph, is one whose the time lag, whose the basin lag rather, is equal to 5.5 times the time step times the duration of rainfall times the duration of the rainfall TR. So TP is 5.5 TR. And for the required hydrograph, the basin lag, and notice the basin lag starts from the centroid, of the rainfall pulse to the center of the peak of the hydrograph. That is the time lag. And normally time lag is, you could equate it to time of concentration. And normally when you have water flowing during the time of concentration, or if you have a rainfall duration that is equivalent to time of concentration, you have a peak. You will have peak flow because most of the areas of the catchment will be contributing. You have the highest peak because most areas of the catchment will be contributing to runoff. So the difference between these two is that the TPR, time lag for the required TPR, is not equal to 5.5 TR. Is not equal to 5.5 TR. Yes, and comparing these two hydrographs, that is the standard unit and the required unit hydrograph, Snyder defined a number of relationships. He defined a number of relationships, and one of them is that the basin lag TP is calculated by multiplying a constant C1, a constant CT, times L, which is the length of the mainstream in kilometers or miles from the outlet of the upstream divide, from the outlet to the upstream of the divide, and LC is the distance in kilometers from the outlet to a point on the stream nearest to the centroid of the watershed. Nearest to the point in the stream nearest to the centroid of the watershed area. And normally CT is given, C1 is given by 0.1 for the English system, that is generally the SI unit, and CT is a coefficient which is derived from gauged watersheds in the same region. CT is a coefficient derived from gauged watersheds in the same region. So essentially, we can easily calculate CTP because C1 is 0.5, but it will be 1.0. It is 1 for English system. Which is 1.0 for English system. Then CT is a coefficient you can derive by studying gauged watersheds. Remember why we use Snyder's unit hydrograph? Because in those hydrographs, the catchment is not gauged. That is why we use the synthetic hydrographs. Now, CT, the reasoning behind synthetic hydrographs is that you study similar catchments and develop empirical relationships. Now, the TP that is calculated is usually in hours. The resulting will be in hours. The second characteristic is the peak discharge per unit drainage area. It is the peak discharge per unit drainage area QP, and it is given by another constant C2 times a constant CP divided by TP that we calculate in the relationship number 1. So QP is C2, which is 2.75. That is in inches when we are using inches, but it is 640 for the English system. And I have to confirm that so that I don't give the wrong equation. What is the English system? The English system of measurement, sorry. Which is the English? Yeah, the English should be the SI units. The English units should be the SI units, so that in the first case, C1, because as we use the English system, C1 is 1. C1 is 1, actually. It's not 0.75. It is 1. I have to modify that, and I have to note it down, otherwise I'll not remember to correct. Correction, C1 is equals to 1. But I have to confirm also whether, what is English system? Metric systems and English systems. The US English system grew out of which people, English, the English and, yeah, let me check. I'm trying to English units. English units were used in England up to 1826. I'm Googling because now I don't want to. Out of the, no, I will confirm later. These coefficients, the values, I will confirm them later. So, because I know in C2, I've said C2 is 2.75, but probably it may be 640. It may be 640 because the English system, it uses 640. So the peak discharge is related with this. So another, and I want you to note down so that if someone can remind me, I need to confirm this value. That value and that value, I need to confirm them because if it is in the imperial units, then we will be fundamentally wrong. And CP is a coefficient derived from gauged watersheds in the same region. And to compute CT and CP for a particular given watershed, the values of LC, L and LC are usually measured from the basin. The values of L and LC are usually measured from the basin map. if you have already a derived unit hydrograph, if you have already a derived unit hydrograph of the watershed, and you already have values of its effective TR, in hours, and you already have the basin lag TPR in hours. You also have its peak discharge per unit drainage area. Then you can develop the relationships. You can develop the relationship that TR is equals to TP and QPR. TR is equals to TP and QPR is equals to QP. TR is equals to TP. This should be TPR. This should be TPR. This TR is equals to, this is T capital R. I need to correct this because I'm actually just checking the graph, and I'm seeing this TR capital R is equals to TR small r, and I need to correct that. This Snyder's graph, Snyder's notes, I need to, this particular one, I need to correct. This is T capital R is equals to TR. T capital R is equals to TR, and then QPR is equals to QP. So essentially we are correlating, what we are correlating is this, we are correlating TP with TPR, TR with TR, and QP with QPR. Essentially, that is what this part. So there is some error here. And then we can also compute CT and CP from the previous equations 3 and 4. We can compute them from equations 3 and 4. Then from that, we can calculate TP. We can calculate TP as TPR from plus TR minus TR over 4. And then you can solve the equation 2 that we stated earlier and equation 5 simultaneously to solve various characteristics of the hydrograph. Notice in this particular kind of Snyder's, we correlate the unit hydrograph characteristics with characteristics of the catchment. What are the characteristics of the catchment here? We have lengths, we have basin time lags, and that is what we are correlating. Now, if you, because we are dealing with engaged catchments, the values, the coefficients T and CP can be derived by assuming coefficients from similar catchments. And then once we use them, those will be able to derive the Snyder's unit hydrograph. So essentially, what this method is doing, we want to derive this unit hydrograph because this is the required. And the minute we do this, if we apply finite differences, if we apply finite differences by assuming we have measured, we can derive point sample data. Point sample data, if you remember what we talked about, if we can derive point sample data from this hydrograph, then, or rather, if we can determine TR, if we can determine QPR, if we can determine TPR, and we can determine W75, we can determine W50, we can determine TB, the basin lag time, then you can draw a hydrograph, and from the hydrograph you can extract sample data, which you can use in the convolution or deconvolution equation. But let's go and finish, because you have to determine also the relationships of W. So the relationship, number 3, the relationship between QP, the peak discharge per unit drainage area, QPR of the required unit hydrograph is given using this relationship, and the base time TB in hours is determined using this relationship. And this relationship is based on the fact that the area under the unit hydrograph is equivalent to a direct runoff of 1 centimeter. And you assume a triangular shape of the unit hydrograph, the unit base time may be estimated using this relationship. And finally, the width in hours of a unit hydrograph at a discharge equal to a certain percentage of the peak discharge QPR is given by W is equals to CW QPR minus raised to power 1 minus 8. And we have additional coefficients here. CW is and here I have to check, because probably this one is for imperial methods, but if it is the English system, I think it should be what, for 40, and I'll confirm that. CW, and it is 770 for the 50% width. So if W is W75, CW will be, I think, for 40, and if it is if W is W50, the CW will be 770. I have to confirm. If it is W50, it is 770, and I have to confirm that. So we have an example. We have an example that is soft. We are given the basin map of a given watershed. We have been given the value of L. We have been given the value of LC. And we have been given a drainage area from the unit hydrograph, where a number of things have been determined. TR is determined as 12 hours. TPR is determined as for 34 hours. And the peak discharge is determined and was as 157.5 meters cubed per second. And we are required to determine the coefficient CT and CP for the synthetic unit hydrograph of the watershed. So that is going to be direct application of equation 5. Equation 5 and equation 4. Equation 5 and equation 4, and then you just solve the problems. But the second example, in the second example, so this will require application of equation 5, and I've said the other equation is equation 4. Equation 4, yes. So In example 2, we go further and actually develop the hydrograph itself. We go ahead and develop a hydrograph itself, and the question says, in the next example, compute the 6-hour synthetic unit hydrograph of a watershed having a drainage area of 2,500 kilometers squared, and with L is equals to 100 kilometers and LC is 50 kilometers. And we are told the watershed is a sub-drainage area of the watershed in the previous example. And in the previous example, we have been able to calculate CT, and we have been able to calculate CP. So how do we go about it? We first calculate TP, we calculate TR, and then using equation 9, is it equation 9? Do we have equation 9 even? That should be equation 5. Using equation 5, and I've written it to be equation 9, because we don't even have equation 9. Using equation 5, we calculate TP, we calculate TPR, and finally from equation 4, we calculate QP. Remember, what are we required to determine? We are supposed to determine, apply those equations so that we can be able to calculate. In order for us to develop the required unit hydrograph, we need QPR. This is the peak flow. We need TB, and we need W50, we need W75. We need W50, we need W75. So that is what we are required to determine. And that is, you will go through the solution. We will go physically through it in class. We'll go physically through it in class with you people, but essentially follow it and see how they have been able to calculate the various components. So let me try to highlight so we need to determine TPR, we need to determine QPR, we need to determine W50 and W75. W50, sorry, W50, and we need to determine W75, and then we need to calculate TB. We need to calculate TB, and once we have that, we can develop the synthetic unit hydrograph, which resembles more like a triangle. And why? Because we have only been able to calculate these particular components, and we do not know how the variability between those 2 points. So we join the points that we have calculated using straight lines. So it is more of a triangular kind of a thing. So this is the synthetic unit hydrograph calculated using the Snyder's Snyder's method. Now, I want to just mention a little bit, about the Snyder's unit hydrograph, and we will stop at the Snyder's unit hydrograph. Go through the two examples, and probably the next class we need to have a physical session so that we can be able to do some practice on the unit hydrograph and also on the Snyder's unit hydrograph. And why do I want that? So that already we can have a feel, because I'll also give tutorials. I'll give tutorials, and at this point, I want us to do some examples, physical examples in class, so that we can see that the process is not difficult. It's as simple as they can come. So I'll mention one thing about a modification or a permutation of the Snyder's unit hydrograph at an effort to regionalize UH parameters. And this attempt was done long time, in 1977. And I can assure you, recently I even was thinking about regionalization of some other hydraulic parameters. It is not as easy as they are speaking, because attempts have been done, and you study, and it is, even when you look at recent researches, this thing is not as easy and as straightforward as it looks. But just to mention it, so these two people, that is SP and Altman, actually there are three, develop a set of generalized equations for the construction of a 10-minute unit hydrograph 14 to 15 miles, and in impervious percentage from 2 to 100%. So 41 watersheds, 41 are located in Texas, 9 in North Carolina, 6 in Kentucky, 4 in Indiana, 2 each in Colorado and Mississippi, and 1 each in Tennessee and Pennsylvania. Now, and you notice I have put that segment in red, and rightfully so, because these equations, they have been developed using watersheds in the United States. We do not know the characteristics. And so, can they be used? To what extent can we use them in Kenya, for example, or in Equatorial Africa? To what extent can we use them in Asia, and such kind of things? And so, especially when relationships have been developed using empirical relationships, the resulting equations or relationships must be used with a lot of cautions. And actually, it is recommended that you use those relationships only in those areas. But what I'm trying to show, and the importance of this is to show you can go further and develop regionalized parameters for the UH, for the Snyder's UH unit hydrograph for a particular region. And in these particular expressions, the phi can be determined from this kind of a graph. And it is a function of channel roughness and water 0 to 100%. So you can estimate your values of phi. And what we have here, is just the explanation or definition of these parameters used in this particular regionalization equations. And that one, basically, I just mentioned in passing. Just for illustration. We are not going to concentrate or discuss that further. If we had some regionalization units for our area, probably it would make sense for us to we will have to it would make sense if the regionalization equations we have there are for our region. So today we will not extend our class because one, I have to be taking my son to school. So I have to prepare to leave. When we come back, next time we will start with SES dimensionless unit hydrograph, which essentially, I think it should be shorter. The relationship are shorter, not a few are not like with the Snyder's. But essentially, you start from, in the Snyder's, we started from a standard unit hydrograph to the real hydrograph and correlating the two parameters, the parameters in the two, unit hydrographs. But here, we will, in the SES method, we have a unit hydrograph developed by SES service, SES of the US. So they have developed a relationship of the unit hydrograph. And from this relationship now, we start from here to part B, the dimensionless unit hydrograph that is of interest to us. So that is what we'll be looking at, trying to relate the parameters in part A with the parameters in part B. Someone is saying here, voted. I don't know. I'm still going to give another vote. So 8:57. And I will still at the end make a snip of those people who are not responding to the votes. And by the way, we are going to modify this voting thing. Nikuwe napeana calls, polls anytime. Because now I'm noticing people wanaenda wanalala, anasema tu atakuja after 1 hour, atakuja after another hour. So now I'll be doing it randomly. So allow us to stop there. And apologies for being late. What was in my head was that I'm supposed to be, taking children to school. And I had thought I had communicated, but last evening I had a meeting that went on for up to late, so that made me forget to highlight or to send notification about today. Nonetheless, we have managed to do something which is a good thing. And thank you for that person who called. Otherwise, I wasn't going to show. So the next poll, let us see. So I will just make a snip of those people who have not responded yet. And then after that, I'll call their names. For example, For example, we have Brian Bisonga, Clive Mogire, Maurice Mongela, Melvin Anthony Kinoti. So normally this is how Angela Wanjiku has responded. This is how I usually tell those people who have just taken us for a ride. So you can see Brian Bisonga was not there initially, and he's also not here. The other one, let me see if we have a repeat offender. It's only Brian Bisonga. Huyo ndio aliamua. Clive ran out of bundles. I'm sorry about that. Bado. Anyway, these things happen. Even sometimes you can have bad network, but normally what I'm emphasizing is try and attend classes. Try and attend the classes. Okay, so I think we stop at this point. Like I even see my connection is even becoming weak, so these things do happen. But we have to try as best as we can to we have to try as much as we can so that we can cooperate and have a successful day. See you again.